Oh, hey there, old friend. It's you again. It's nice of you to join me. Today we're going to be talking about posits. We'll also be talking a little bit about algorithms, which is why I'm drinking from my algorithm cup, and I'll bring it closer so you can see. It'd be funnier if I was drinking coffee, but regardless, we have a lot to do today, so let's get started. And you may be wondering, why are hash diagrams even important? They're just a bunch of scribbles, and they are a bunch of scribbles, but they're important for two reasons. The first, and the most important, is that they'll be on your next quiz. But the second reason they're so important is that computers actually cannot solve many problems in a reasonable amount of time. Some problems would take millions of years for a computer to solve, but certain types of graphs, such as those that hash diagrams are based off of, allow us to solve many problems, which we won't be going over. Did you know there are actually many different types of graphs other than digraphs and hash diagrams? It's true. This will not be on your quiz, and you will never be tested on this. But I thought it'd be interesting to go over some of them before we got started. This, for example, is a triangulated graph, right? You see a bunch of triangles. This graph, for example, is a caterpillar, and it really is. You can Google it. Now this is a Mongolian tent, a lobster. I kind of see it, right? This is a binary tree. If you've never heard of one of these before, then you will in later courses. Now this is one of many snarks. Let's begin with the first problem, which are posits. All right, so we're given the following relation, 0, 0, 2, 2, and 3, 3, and we know the set of numbers or elements is 0 through 3. So first we determine whether it is reflexive, and clearly it's not. We have 0, 0, we have 2, 2, we have 3, 3, but we do not have 1, 1, right? And that's one of the values within our set that we're given. So, no, because 1, 1 is not in the relation. So at this point, we already know this relation is not a posit because it's not reflexive. It must be all three of these to be a posit. However, we can continue. Let's also determine whether it is antisymmetric and or transitive, just to test ourselves. Recall the definition of antisymmetry. So recalling this definition, let's determine whether there are any pairs within this relation in which the left-hand side does not match the right-hand side. And well, there are none. There are no pairs in which A does not equal B. So the left-hand side of this implication is automatically false. And when the left-hand side of an implication is false, then it doesn't matter what the right hand of the implication is, whether it's true, whether it's false. We don't even have to check, because the implication automatically holds true. In the same sense, because there are no pairs to check antisymmetry on, antisymmetry holds automatically. Finally, is it transitive? And well, for the same reason that it is antisymmetric, it is transitive. We don't have any two pairs in which the right-hand side of the first pair matches the left-hand side of the second, so it automatically passes transitivity. We're given the following relation. So right off the bat, we can see it is obviously reflexive. It has 0, 0, 1, 1, 2, 2, and 3, 3. Now, is it antisymmetric? Well, let's check all the pairs in which A does not equal to B. So that would be 2, 0. So if 2, 0 exists, then 0, 2 should not exist. And it doesn't. We have 2, 3. This means 3, 2 should not exist. And it doesn't. So in all cases, antisymmetry holds, therefore the relation is antisymmetric. Now let's check transitivity. Well, transitivity is pretty easy to check here. For example, we have 2, 3. The 3 matches with the left 3 on this pair here. 2, 3 and 3, 3 imply the existence of 2, 3. and that's already handled by this relation, or this pair right here. So this holds true in all cases, in fact, and therefore this relation is transitive. And because it's all three of these, we would say yes, this relation is in fact a posit. Okay, moving on to the next one, just looking at it carefully, we can already tell that it is reflexive and it is also antisymmetric. But transitivity is a little trickier. So within a relation, we see the pair 3, 1. We also see the pair 1, 2. So let's write those down. We have 3, 1 and we have 1, 2, which are both in the relation. Now this implies the existence of 3, 2. This should also be in the relation. But 3, 2 is not in the relation. So therefore the implication fails, and because the implication fails on transitivity, we would say this relation is not transitive, and therefore it's not a posit. So for the following relationship, is it reflexive? We have 0, 0, we have 1, 1, we have 2, 2, and we have 3, 3. Therefore it is reflexive. Is it antisymmetric? Well, we have 1, 2, and we do not have 2, 1. We have 1, 3, we do not have 3, 1. We have 2, 0, and there is no 0, 2. We have 2, 3, there's no 3, 2, and we have 3, 0, and there's no 0, 3. So there are no symmetric pairings. Therefore, antisymmetry does in fact hold. So we would say yes, this relation is antisymmetric. Okay, is it transitive? Well, let's copy that an example. We have 1, 2. We have 2, 0, both in the relationship. Now this implies the existence of 1, 0, but we don't see 1, 0 anywhere. It's not in the relationship, implication fails, so no, our relationship is not a transitive and not a posit. Is S, R a posit, where S is the set we're given, that is the set of all people in the world, and R is the relation we're given, where A, R is in the relation, where A and B are people, if the following holds true. A weighs more than B. So first, we need to determine whether this is reflexive. That is to say, does it make sense to say A weighs more than A, right? So that would be the reflexive statement, to replace the B with A. A weighs more than A. And does that make any sense to say that you weigh more than yourself? Well, no, that makes no sense. So we would say it's not reflexive, because it makes no sense for A, A to be in the relationship. So that means this relation is not a posit, given the following statement. A equals B, or A is a descendant of B. Now, the reflexive property is automatically passed by the given statement here, A equals B, or. So, because this is given to hold true, we would say yes, this relationship is in fact reflexive. Now we need to determine whether it's antisymmetric. So let's plug in some names for A and B. Let's say that we have Bob, who is A, and maybe Jill, who is B. Now if Bob and Jill are in the relationship, that is to say that Bob is a descendant of Jill, then this should imply that Jill is not a descendant of Bob. That is to say, Jill, Bob is not in the relationship, right? Now, if Bob is a descendant of Jill, then Jill cannot be a descendant of Bob. I mean, they can be related, but one can't be a descendant of, they can't be descendants of each other, right? That's not how that works, so no, this relationship is not symmetric. It is in fact antisymmetric. So anti-symmetry does hold as well. Next, we need to determine whether it's transitive. So remember with transitivity, we have A, B, and C. So let's make up three names. Let's say we have Bob, who is a descendant of Jill, and this exists in the relationship. We also have that Jill is a descendant of, well, I don't know, is a descendant of Ryan, okay? And this is also in the relationship. Now, does it make sense to say that Bob is a descendant of Ryan? Right, well, all we're doing is cutting out Jill. We're just saying that Bob is a descendant of Ryan, through Jill. And because of that, transitivity holds. So this implies that Bob is a descendant of Ryan. And this does in fact hold. So yes, this relationship is transitive as well. Because it's reflexive, antisymmetric, and transitive, we would say yes. This relationship is a posit. A and B do not have a common friend. Okay, so first we determine whether it's reflexive. This is to say, does it make sense that Jill and Jill are both in the relationship? This is not true, right? Because anyone, for example, Jill, does have a common friend with themselves. So it's not in the relationship. By counterexample, this relation is not reflexive and therefore not a posit. We're going to keep going. Again, we determine whether this relationship, given the set A, B, C, and D, is a posit or a partial order. Now, I already wrote A, B, C, D on the rows and A, B, C, D on the columns, so that should make it a little easier. But first we determine whether it's reflexive. And, well, clearly it's reflexive. All of the diagonals are ones, so therefore reflexivity does hold. Now, is it antisymmetric? Well, we look at every one which does not lie on the diagonal, and we check whether there's a corresponding 0 on the other side of the diagonal across the fold. This one corresponds to a 0. That's good. This one corresponds to a 0. Check. This one corresponds to a 0 as well. And finally, this one corresponds to a 0 below the diagonal. Antisymmetry holds in all cases, therefore this relation is also antisymmetric. Now let's determine whether it's transitive. Okay, well, we have, for example, B comma C. We also have C comma D. So we're looking at the third column and the third row. Every intersection with these two ones should be a 1 as well. However, if we go up and across, we see that these two ones intersect at a 0. This should be a 1 if this relationship was transitive, but it's not. This is a 0, so transitivity does not in fact hold. For example, we have B comma C, we have C comma D, both in the relationship, but B comma D is not in the relationship. So by counterexample, this relationship is not transitive and not a posit. So now we get to my personal favorite part of the semester, drawing some graphs. So the question reads, draw a Hasse diagram for divisibility on this given set. And it gives us a set. We know our relationship is going to be divisibility. So at every step along the way, we're going to check divisibility. So right now we don't have a graph. So beginning from the left of the set, all we're going to do is add the first element. At the very bottom level of the Hasse diagram, we're going to draw a node and label it 2. All right, so 2 is done. We move to the right. We look at 3 and we ask ourselves, is 3 divisible by 2? Well, the answer is no. So we put 3 on the lowest level right next to 2, and 2 and 3 do not have a relationship, so we don't draw an edge between them. Okay, next we have 5. Is 5 divisible by 2 or divisible by 3? Well, no, 5 is not. So again, we draw 5 at the bottom and do not denote a relationship from 5 to 3 or to 2. Okay, then 10. Is 10 divisible by 2, 3, or 5? Right, it is. So we draw 10 on the second level and we connect 10 to 2 as well as to 5, because 10 has a relationship through divisibility to 2 and to 5. Okay, we go on to 11. 11 isn't divisible by any of these, so 11 goes at the bottom. 15 goes on the second level, and 15 is divisible by both 3 and 5. Finally, 25 is divisible by only 5, and this completes our hash diagram. It's okay that 11 is on its own, we still include it, it just doesn't have a relationship through divisibility to any of the other elements. Let's answer the following questions given this posit over here. So this follows that same S(R) notation. On the left we have a set, and on the right is the operator that we want to show is a posit using these elements. So we begin by drawing a hash diagram. Remember, because we don't have anything yet, we begin with the leftmost element on its own at the very lowest level of this hash diagram. Next, we look at 4. 4 is divisible by 2, so we draw 4 on the next level with an edge to 2. 6 is divisible by 2, but it is not divisible by 4, so we don't draw an edge from 6 to 4. Next, 9 is not divisible by any of these, so it's on its own at the very bottom on the same level as 2. 12 is divisible by both 6, 4, as well as 2. Now remember, hash diagrams represent a posit, and a posit has transitivity, which means that 12 is divisible by 2 through 6 or through 4. So we don't draw an edge from 12 to 2 because that edge is implied by transitivity. From there, we're given 18. 18 is divisible by 6 and by 2, but is not divisible by 4 or by 12. So we don't put them on, we don't put it above 12, and we don't draw an edge from 18 to 4. Of course, just as much, 18 is divisible by 9, so don't forget 9 over here. He was getting pretty lonely. Okay, 27 now is divisible only by 9. 36 goes up here, is divisible by 18, 9, 6, 12, 4, and 2. Finally, we have 48, 60, and 72, as follows. And this completes our hash diagram. And let's answer the following questions now. What are the maximal elements? Well, the maximal elements are simply the elements which don't have any nodes above them. So for example, that would be 27 because there's nothing higher than 27 that it's connected to, 72, 48, and 60. Now, what are the minimal elements? Well, it's the same thing, but from the bottom. So that would be 9 and 2. There's nothing lower than 9 and 2. Now, is there a greatest element? And the answer is no, there is no greatest element because there are multiple maximal elements. We have 27, 72, 48, and 60. A maximum element is one that is higher than all the others, that everything leads to. But of course, none of these would satisfy that condition, right? Because there are many elements that don't lead to 27, and of course, there are some elements that don't lead to 72, 48, and 60. So there are no maximum elements. Similarly, there are no least elements because there are 2 nodes at the bottom. There would be a least element if we had one more node below both that everything kind of funneled down into, but we don't have that. So there is no least element. Let's determine what are the upper bounds of 2 and 9. So these are simply the nodes that are above 2 and 9, which they both share. These are elements that are divisible by both 2 and 9. That would be 18, 36, and 72. We can see that because we have to go down to reach a 9 through any one of these, and we have to go down to reach 2 from any one of these. 4 would not be an upper bound, because although 4 is divisible by 2, 4 is not divisible by 9. We have to go up and then down to reach 9 from 4, so it doesn't have a relationship. Okay. What are the least upper bounds of 2 and 9? Well, that's just the least element of the upper bounds, which would be 18. Now, what are the lower bounds of 60, 72? Okay, it's the same thing, but in reverse. We have 60, we have 72. What can divide both of these elements? Well, that would be 2, 4, 6, and 12. 18 would not divide 60, and we can see this just by looking at the hash diagram. We have to go down from 60, up, and then down again to reach 18 from 60. It's only a lower bound if you can go straight down to that element. So that would be 2, 4, 6, and 12 again. Finally, what is the greatest lower bound of 60, 72? Well, again, that would just be the greatest element of the lower bounds, which is the 12. Find a compatible total order of the following diagram. Okay, that's easy. We do this by playing eeny, meeny, miny, mo. We look at all the minimal elements, and then we just randomly choose whichever we feel, and then remove it, and add it to the beginning of our total order. It's very easy. So we'll play eeny, meeny, miny, mo, and choose either A, B, or C, because any one of these is a minimal element of the following diagram. And, I'll just randomly remove A. A goes to the start of our total ordering. Next, we have two minimal elements, B or C. Let's remove B. Next, let's remove C. Okay, now we have three minimal elements again, D, E, or F. Let's remove D. Then we have I, E, or F. Let's just go with E. Let's go with F next. Next we have I, H, or G, but let's go with the G. Let's go with H. Then we have I. From there, we have two minimum elements. We have J or K. We can remove the J next. Now we only have one minimum element, which is the K, so we must remove the K. Then we can remove them in either order because they're both minimum elements. Let's do L and then M. And then we're finished. This would be our total order of the hash diagram that used to be there. Okay, that concludes the section on posits and graphs. If you have any more questions regarding those kind of graphs or any other kind of graphs that you're curious about, then you should come to my office hours. I'm very lonely there. Let's describe an algorithm that takes as input a list of n integers and produces an output, the largest difference obtained by subtracting an integer in the list from the one following it. Okay, so this is an algorithm. So before we even begin the algorithm, let's just begin by writing out the definition, kind of the blueprint, the name at least. So let's call it a procedure. This is also just like a function. It's pseudocode, so it doesn't have to fit any particular programming language. From there, let's call it the largest difference. And it takes as input a list of n number of integers. So let's begin from a of 1 all the way through a of n. And these, of course, are integers. From there, let's define a maximum value. So at the beginning, what is our maximum? Well, it'll be 0. So let's make a variable and just say it's equal to 0, just to start out with. Okay, from there we're going to have a loop, right? We need a loop through all of our elements. So let's begin at 1, right? We're beginning 1 here, not at 0. We could have begun at 0 if our pseudocode had been like that, but we're going to begin at 1. We're going to say for some variable I, which begins at 1, up through 2, and minus 1, the following occurs. If maximum, as it currently is less than a of I plus 1 minus a of I, then do the following. Maximum will be updated. It becomes the difference between the next value and the current value, right? So at every step of this for loop, we're comparing the current index within our given array or list with the next one. We're taking the difference from the next one, so it's I plus 1, with the current one, just a of I. And if that difference is greater than the current maximum, then maximum is updated to be that new difference. Okay, so to end our algorithm, we're going to return. So we want to return maximum, right? So let's return whatever maximum is when we're finished with this for loop. So we need to determine whether an input string is a palindrome. And of course, a palindrome is a string that reads the same forward and backward, like race car, for example. I already wrote the procedure. We're going to call it palindrome checker, and it takes as input n characters, 1 through n, and this denotes a string. Let's begin by assuming whatever is input is currently a palindrome. We're going to do a loop. We're going to say that we begin at I, which is equal to 1, the first character in our string, and this goes all the way through to the floor of n over 2. We're only going to check up to the halfway point. Of course, if we have an odd string input, that halfway point could be a decimal, so we're going to round down in those cases, which is why we use the floor function. Next, we have an if statement. If a of I does not equal a of n plus 1, n plus 1 being the very far right, the end of our string, minus I, then our answer becomes false. And then we can continue looping through. It's already false, so it'll never become true again, but when the for loop is over, we're going to return whatever that answer was, whether it's true, that it's a palindrome, or false, it's not a palindrome. And let's show an example to show that this works. Let's say we have, for example, race car. On the first iteration, I is 1, so we're going to check a of I. A of I is currently dr. We're going to check whether it is or is not equal to a of n plus 1 minus I. Now, a of n plus 1 is at the very far end of our string. It's past the endpoint. A of n plus 1 minus I will subtract the current iteration. So what is a of n plus 1 minus 1? Well, it lands on the other r at the end of the loop. Now, on the second loop, we would have a of 2 being compared with a of n plus 1 minus 2. So that a would be compared with that a. And once we got to the halfway point, we would stop, because we know the e, it doesn't matter whether it matches anything, because it's the halfway point, so it matches itself. And at that point, it breaks the loop and returns our answer. Now, if, for example, we were comparing race cat or something like that, the r would compare with the d. This if statement would pass, and it would change answer to false, so it would not be a palindrome. At that point, it would continue checking all of the inner elements, but it would never determine that this answer can never become true again. So our answer would be false in this case. Okay, we want to determine an algorithm that finds the first term of a sequence of positive integers that is less than the immediately preceding term of the sequence. So let's say, for example, we have some input. Let's say that input is like 1, 3, 4, 2. 1 is less than 3, it's fine. 3 is less than 4, that's fine. But as soon as this algorithm gets to 2, it says, hey, 2 is less than the preceding element. Let's return 2. Okay, so that's kind of how that algorithm works. We want to determine the location. So let's begin by saying location is currently 0. We'll call it LOC for location, and it begins at 0. Because we won't be returning the element itself, we'll be returning the position of the element within this array. All right, from there, let's just say that I is currently equal to 2, right? It's 2 and not 1 because we wouldn't compare the first element to anything before it, right? That would be a bug in our code. From there, we have a while loop. Let's say while I is less than or equal to n, and the location is currently equal to 0, we do the following. If a of I is less than a of I minus 1, then we update the location. We see location is equal to whatever the current iteration of the loop is, which is I. And this, of course, a of I less than a of I minus 1 is saying that the current element, the current iteration, is less than the previous element within the array. All right, and if this is not true, then we're going to say I is equal to I plus 1. I mean, we could have just done a for loop, but we can do while loops as well. They're pretty fun. Okay, regardless, whatever happens here, once it reaches that location is equal to I, it knows location is not 0, so this while loop will break. And from here, we simply return the location. And this will solve for this algorithm. Okay, we want to use a greedy algorithm to make change for these coin amounts. We're only allowed to use quarters, dimes, and pennies. There are no nickels. And then we want to determine which of these uses the fewest number of coins with the greedy algorithm. All right, so let's begin with A. We just subtract the largest coin possible. So it wouldn't be pennies or dimes, but it would be quarters, because quarters fits multiple times into 87 cents. So if we subtract 75 cents, that's 3 quarters, we're left with 12. From there, we can subtract 1 dime, we get 2, then subtract 2 pennies, which gives us direct change for 87 cents. We used 3 quarters, 1 dime, and 2 pennies for a total of 6 coins for part A. For part B, we can plug in 1 quarter. We get 24 cents left. From there, we can plug in 2 dimes for 4 pennies left. Minus 4 pennies is direct change for 49 cents. That used 1 quarter, 2 dimes, and 4 pennies. So using the greedy algorithm, it requires 7 coins to make change for 49 cents. Next, we have part C. First, we would plug in 3 quarters. So that's minus 75. We're left with 24 cents. Again, we plug in 2 dimes and 4 pennies. So that's 2 dimes and 4 pennies to give us direct change for 99 cents. In total, that uses 9 coins to make change for part C. Now for part D, we plug in 1 quarter, we get 8 cents left. We can't plug in nickels, so we have to plug in 8 pennies. Minus 8 gives us direct change. That also used a whopping 9 coins to make change for part D. Now, the lowest of these is part A. So part A would be the answer for the least number of coins, or the fewest number of coins to make change using the greedy algorithm. Okay, I'll see you next time.